Welcome back. Next we're going to look at numerical errors in solving linear equations. And so we're going to be looking at an equation ax is equal to b. And the thing that we're worried about is the fact that very small changes in b can lead to very large changes in x. And if that's the case, then a small error in measurement or computation can have disastrous consequences. So let's illustrate this with an example. Take A to be this matrix. It's close to 1, 1, 1, 1, but there's a little change in the lower right-hand corner. Now, if B is the vector 2, 2, you get this equation. And let's solve this. Well, of course, it's Gaussian elimination. Subtract the first row from the second, and you get the equation like this. And now that 0.001 in the lower right-hand corner says that y has to be equal to 0. And the solution to this equation is, therefore, x is equal to 2 and y is equal to 0. Fine. Now let's go back and suppose that you perturb b ever so slightly and replace 2 with 2.001. Then the equation is this, and when you do the same Gaussian elimination step, you get the same thing, except that in the very last, in the target matrix, that 0 becomes a 0.001. And the consequence of that is that y is equal to 1. And x is equal to 1. Okay, well, I hope you see what a problem that is. This very tiny change to b had a dramatic change to x and y. It went from 2, 0 to 1, 1. So that's a huge change compared to 0.001. And that means that this is a bad matrix and you need to be careful if you were trying to solve equations involving it. Okay, so let's quantify this. Let's make this whole issue a little more precise. So we're solving ax is equal to b. And now let's suppose we perturb b a little bit. We replace b with b plus epsilon, where epsilon is some small vector pointing in some direction. I don't know where, just somewhere. And the consequence is that x is going to be replaced with another vector, x plus delta. And the question is, how big is delta going to be? The addition of epsilon causes x to be perturbed by delta. That is to say, the new equation is ax plus delta is equal to b plus epsilon. And that's ax plus a delta is b plus epsilon. And of course, ax is equal to b, so you can cancel those terms. And we have that a delta is equal to epsilon. So that's fine. What we want to look at is the ratio of epsilon to delta. Or, as I said here, epsilon versus delta. But what's better is the following. We'd like to normalize what we're looking at. And the reason is that if you scale this equation, it doesn't really change anything. So that is, if you replace a with c times a and b with c times b, it's the same equation, but it would scale both epsilon and delta. So we want to get rid of that. And so the way we do that is, rather than looking at epsilon and delta directly, what we want to look at is the following. We want to look at the length of epsilon over the length of b versus the length of delta over the length of x. So those denominators are the normalizing factors. And what's bad is if this term is big, but the second term, the first term is small, but the second term is big. That's what we're worried about. So let's look at the ratio of these two things, the second thing over the first thing. We want this number to be small. Small is good here. So that's what we're going to talk about a little bit. How do you estimate, or what can you say about the size of this ratio? And notice that a smaller delta and a bigger epsilon both make this thing smaller, which is the right idea. Small epsilon and big delta, small delta and big epsilon is good. So now let's look at an example. Suppose A was diagonalizable, and let's say real eigenvalues, not that it really matters. And suppose you let vi be the eigenvector, which is to say AVI is equal to lambda I VI. Well, this is the original equation. VI is playing the role of x, and b over here. And so what I see is that the length of x is equal to the absolute value of lambda times the length of b. So that is to say the length of b over the length of x is the absolute value of lambda. So the size of lambda is what's important here. Well, there are all these different lambdas, and we don't know what they are, but the point is that what we can say is that the length of b over the length of x is less than or equal to the absolute value of the maximal lambda. And we want this number to be small, so that's why I'm writing less than or equal to something. So let's go back and show where I'm going to use this. We were looking at making sure this thing was small, and I'm just going to rewrite this fraction as a product of two different ratios. The first one involves delta and epsilon, and the second one involves b and x. And here we have this b over x, which I was just talking about, and I have a bound on that. It's less than or equal to the absolute value of lambda max. Now, what about this first term? Well, it's basically the same thing. It's a delta is equal to epsilon instead of ax is equal to b. So exactly the same consideration says that we can tell that absolute value, norm of epsilon over norm of delta is less than or equal to absolute value of lambda max. But what's over here in this, what I'm looking at is it's upside down. I have delta over epsilon here, not epsilon over delta. So I need to turn this thing upside down, and what happens is I get, when I take the inverse, and I flip this term, well, the inequality turns around, so I get absolute value of delta over absolute value of epsilon is greater than or equal to something. And that's not what I want. I'm trying to make sure this thing up here is small, so this is not useful. But, well, the point is that you should just be using the smallest eigenvalue. The similar argument says that the norm of epsilon over norm of delta is greater than or equal to lambda min. So when you turn that upside down, you get an inequality of the type that you want. And this ratio is less than or equal to 1 over absolute lambda min. Okay, so this thing that we're trying to make small up here, we now have a bound on it. It's less than or equal to, well, we have 1 over absolute lambda min and absolute lambda max. So clearly the maximum and minimum size of the eigenvalues are what's important here. So the conclusion is the following. This number that I'm trying to put a bound on, this ratio of ratios, is less than or equal to the absolute value of lambda max over the absolute value of lambda min. And I would really like this to be small. So what's bad is when lambda max is big and lambda min is small, or both of those things, so that the ratio is big. All right, so let's look at our example that we had before. The matrix we were talking about was 1, 1, 1, and this 1.001. Well, this is very close to 1, 1, 1, 1, and this has eigenvalues 0 and 2. So when you perturb this matrix, the eigenvalues are close. They vary just a little bit, so they're going to be close to 0 and 2. And if you calculate them, in fact, they turn out to be 2.0005 and 0.0005. And that ratio is about 4,000, which is enormous. So that's why this is a bad matrix. Okay, so that motivates the following definition. If A is a symmetric matrix, and it's important that A be symmetric here, since it's symmetric, it has real eigenvalues. And you define the condition number of A to be this ratio, absolute value of lambda max over absolute value of lambda min. And the condition number is it's a measure of how good A is, and we say A is well conditioned if this number is small. Okay, so that's a good notion of good matrix when A is symmetric, the condition number being small. What if A is not symmetric? Well, then its eigenvalues aren't necessarily real, but in any event, the eigenvalues aren't particularly useful in this situation. And let's look at an example. This is something we looked at earlier in a slightly different setting. Consider this matrix with 1s on the subdiagonal and some small epsilon in the upper right-hand corner. Well, you should think of epsilon as being 0, but then it might be perturbed. And when epsilon is equal to 0, all of the eigenvalues are 0. But this is a terrible matrix. I used this as an example earlier to show that epsilon dramatically affects the eigenvalues of this matrix. And it's easy to see it also dramatically affects solutions to an equation AX is equal to B. So let's look at an example of that. Let's just do a 3x3 example. Suppose you had this matrix and you're solving AX is equal to B, where B is 0, 1, 1. The solution is easily seen to be X is equal to Y is equal to 1 and Z is equal to 0. Okay, so now let's perturb the B by changing 0 to epsilon. And now it's easy to see X is still equal to Y is equal to 1, and now Z is equal to 1. And that's what's bad. Z jumped from 0 to 1, even though epsilon could be really tiny. So again, that's an example of bad behavior. And we need to somehow detect this in a non-symmetric matrix, so we need some kind of alternative to the condition number. So the idea is the following. We're looking at AX is equal to B. Well, let's suppose for the moment that A was diagonal. And then suppose it had some maximal eigenvalue lambda. Well, the thing that I'm concerned about is the length of B over the length of X, which is to say the length of AX over the length of X, which is simply the absolute value of lambda. And the largest value that this takes is lambda max. And big lambda means that this number is big, which is bad. So what that suggests is, well, we don't have an eigenvalue lambda, but we can use this other thing. Define the norm of A to be the max of AX over the norm of AX over the norm of X. Over all vectors X, and this is called the norm of A. And this is exactly what this is a very good measure of how well-conditioned a matrix is. So again, if A is diagonalizable, you see that the norm of A is exactly the absolute value of lambda max. And also, assuming A is invertible, the norm of A inverse is 1 over the absolute value of lambda min. And so you see that if you take the product of these two, you get the condition number. So that leads to the following definition. The condition number of an arbitrary matrix A is the norm of A over the norm of A inverse. Okay. And the point, well, one of the points is that if the matrix is symmetric or even just diagonalizable, this agrees with the previous condition, lambda max over lambda min. Now, that's all fine and good, but the problem is how on earth do you compute this thing? So you're trying to compute the max of norm of AX over norm of X, and you have to look at all vectors X. I mean, how that's not an easy thing to do. So it seems that abstractly it's a useful definition, but it doesn't look like it's practical. But in fact, it's not so bad. And you just make the following simple observation. If you square the norm of A, what do you get? Well, you get the max over all x's over the norm of AX squared over the norm of x squared. And that is to say it's the max over all x of x transpose A x over x transpose x. And now the key point is that A transpose A is symmetric. And so it's easy to see that the maximum of this thing I've written down here on the right-hand side is going to be simply the maximum eigenvalue of this symmetric matrix A transpose A. So in effect it's reducing us to the previous case of a symmetric matrix. So what you conclude from all of this is that the norm of A is the square root of the largest eigenvalue of A transpose A. So that's a perfectly reasonable thing to compute. And that's a good place to stop. I'll see you in class.